Hi, everyone. Before, we've been talking about things like a sub n equals, uh, well, what, remember -1 to the n times n or something like that, right? Kind of like a function of n. This was a closed form formula. Or you can find a sub a million, right? Plug in a million and you get positive a million. This is a closed form formula. Now, sometimes sequences are defined recursively. We saw that before. You can think of the factorial sequence. A sub n equals n factorial. Where you can actually start with n equals 0, actually. 0 factorial equals 1, and then n factorial. To get this factorial, you take the previous factorial, n minus 1 all factoria, and multiply by the new number. Remember, and you can plug in some small positive integers to look at some examples. What's 4 factorial, right? It's 4 times 3 times 2 times 1. But wait a minute. What is 3 times 2 times 1? What is 3 times 2 times 1? It's 3 factorial. So this is an application of this where n equals 4, but this applies to any positive integer n. Recursive definition. You can go from 0, well, as we've said before, you can go from 0 factorial to 1 factorial, to 2 factorial, to 3 factorial, to 4 factorial. Okay, here from 1 factorial to 2 factorial, you multiply by 2, and then you multiply by 3 to get 3 factorial, then you multiply by 4 to get 4 factorial, multiply by 5 to get 5 factorial, and so forth. So you're building up the sequence instead of just plugging in a number. Now, the problem with this, though, is that if you just have a recursive definition, it could take you a really long time to get to a sub 100, for example. Whereas if you had a closed form formula, it'll be a lot easier if the formula is reasonable. All right. So recursive definitions, it might be okay for the first few terms, but then for a sub 100 or a sub 1,000, you may have some problems. So hopefully we can get a closed form if possible. All right. Now, the most famous recursively defined sequence is a bit more complex, actually. All right. Here's a good Facebook problem, right? What's the next number in the sequence? 1, 1, 2, 3, 5, 8, 11. Wait, I'm sorry. It's 13. Can't add. Okay. Well, what's the pattern? I kind of gave it away with my mistake. What's the next number? I kind of gave it away with my mistake. 1 plus 1 is 2. 1 plus 2 is 3. 3 plus 5 is 8. 8 plus 5 is 13. And 8 plus 13, that's going to be 21. And so on. So our seeds, we have 2 seeds. We start with 2 1s. And then you keep, to get the next number in the sequence, you add the 2 previous numbers. The Fibonacci sequence, very famous. This is probably the most famous recursively defined sequence. Now, there is a closed form formula for this, right? There is a closed form formula. No, and by the way, there's a closed form formula, and it's like this. A sub n equals this horrendous looking thing, which you actually work out in a discrete math class, actually. Now, of course, you don't have to do anything with this. I'm just saying, even this thing, which doesn't seem like it has a nice closed form formula, Well, maybe it doesn't. It has this. It's not that nice, but it does have this. Okay, but this is one thing you try to do in higher math classes. Given a recursively defined sequence, find a closed form formula. Right. And there are many sources on the Fibonacci numbers. So if you want to find a sub 1,000, I guess you'll have to plug it into this formula. It'll take a long time to do it here. Now here's a simpler recursive sequence. Consider the sequence defined recursively by a sub 1 equals 10, and a sub k plus 1 equals twice a sub k, where k is a positive integer. Wait, what does this mean? This means that the initial term, a sub 1, is 10. Well, you got that, okay? Yeah, the first number is 10. I think we got that. But what is this saying? This is saying that every time you want the new number in the sequence, you take the number you're currently at and you multiply by 2. Find the first 3 terms of the sequence. Go. Well, basically you're doubling. You're doubling the current term to get the next term. When you double 10, you get 20. When you double 20, you get 40. Now, if you want to do it more brute force, a sub 1 is 10. A sub 2, if k equals 1, remember k could be any positive integer. If k is 1, then k plus 1 is 2. All right. A sub 2 is twice a sub 1. 2 times 10 is 20. So you could do it this way, more brute force. All right. For a sub 3, okay, it's twice a sub 2. It's twice the 20 here. So you get 40. So you could use this very directly, or you could look at this and go, is there a basic way I can say how I can get from one term to the next? In this case, you take the current term and double it to get the next term. Now, if your formula here is more complicated, then you're going to have to pretty much plug in. Okay. Next up, summation or sigma notation. And before we do that, I want to go back here and show you the recursive definition for this thing. So here, a sub 1 is 1. A sub 2 is 1. These are our 2 seeds. And then, a sub k equals a sub k minus 1 plus a sub k minus 2. Where k could be 3, 4, 5, and so forth. Integers greater than or equal to 3. All right. And that'll be the recursive definition. Basically, I'm saying that, let's say we want to find out what the kth term in the sequence is. Okay. To do that, we have to add the 2 previous terms. You have to add dad and grandpa, or mom and grandma. So to get the kth term, you have to add mom and grandma. To get the kth term, you need to add the k minus 1 term and the k minus 2 term. These indices correspond to the order number in here. Here's okay, as far as k goes. Well, k is 1 here, k is 2 here, k is 3 here. That's the first one where you can apply this, and so forth. All right. Oh, and also, I forgot my Olympics joke way back here before we get to the summation and sigma notation. Remember the Olympics? All right, in China, seriously, if you're a Chinese Olympian, if you come in second, you may as well have come in last. If you're a Chinese Olympian from China, you got to come in first. If you're not a gold winner, you're a loser. It's very, very awful. Okay, next time, summation or sigma notation.